I'm here just to welcome you to the Simon Center for Geometry and Physics. As you know, there are many events going on at the same time here. So first and important is that we celebrate Chris Bishop's birthday. Happy birthday, Chris. And of course, as a part of this celebration, we have a workshop in dynamics. And many people here are participants of this workshop. Welcome again. And this is the joint Simon Center in Mathematics Colloquium. And our speaker today is Scott Sheffield, and as an appreciation for preparing the more popular talk than usual, we give souvenir from Simon Center, which is a laser pointer.
Thank you.
Thank you, Scott. But this is not real introduction of Scott Sheffield. For the real introduction, I'll give the microphone to Ron.
Thank you. I don't have much to add, other than introducing Scott Sheffield, who's going to talk about smooth planar maps and Laplacian determinants.
Okay, thank you very much. It's a great pleasure to be here, especially on the occasion of Chris's birthday. So this is joint work with 3 PhD students at MIT, Morris Ong, Min-Jae Park, and Josh Pfeffer. I want to start with a little conversation that happens once in the world, somewhere in the world every 5 minutes or so. Okay, and it starts like this. Alice says, I learned a cool identity. 1 plus 2 plus 3 plus 4 plus ... is minus 1/12. Bob says, that's wrong. How does that make any sense? Okay, you've all heard this conversation before. Alice says, well, the Riemann zeta function, you have a to s is 1 to the minus s plus 2 to the minus s plus ... That makes sense for real part s greater than 1. Analytic continuation gives a to minus 1 is equal to this. Okay? Seems fairly straightforward. Bob says that is so wrong. Alice says also 1 times 2 times 3 times ... is the square root of 2. Okay, Bob, seriously wrong. Alice says, well, you know, a to prime s, this one I'll write up on the board too, so we have it. So let's see, so what did I say at the beginning? So I said zeta of s is equal to 1 to the minus s plus 2 to the minus s plus ... If we take the derivative of this thing, so zeta prime of s is equal to, so we know how to take derivatives, right? So it's just there's going to be like a log of 1 times 1 to the minus s, maybe minus log of 1, minus log of 2 times 2 to the minus s, minus log of 3 times 3 to the minus s, etc., which means that minus eta prime of 0, zeta prime of 0 is log 1 plus log 2 plus ... which I guess means the e to this is 1 times 2 times etc. So e to the zeta prime of 0 is equal to 1 times 2 times 3 times ... And, well, okay, so you can look it up. This is minus log of root 2, so this thing comes out to be, or 2 pi, so this is square root of 2 pi. Okay, so there you go. Infinity factorial is square root of 2 pi. How many knew already that infinity factorial is root 2 pi? Okay, a few of you, right? A few of you knew that. All right, okay. So, and then Alice says, well, in fact, more generally, if a to I grows linearly, and you write z of s is the sum of lambda j to the minus s. So just extend this, you know, replace the integers with some other equal sequence. So lambda j, which grows roughly linearly, let's say, to make it simple. So asymptotically, it's linear. So z prime of s is going to be, well, let's say, sorry, z of s is just going to be the sum of these lambda j to the minus s, which means that z prime of s is, well, okay, it's the sum of, so minus log lambda j times lambda j to the minus s And, well, somehow you want to say that e to the minus z prime of 0 is equal to the product of lambda j. Okay? And as this conversation continues, Alice says, well, all right, this is obvious for finite products. So if we define z of s for real part of s greater than 1 and analytically continue, then it also works in the infinite limit. Okay? Bob says that's not how limits work. Convergence on real part of s greater than 1 is not the same as convergence at 0. Alice says, well, no, not in the conventional sense, but it is useful, for example, in string theory to interpret these identities as being true in an alternative sense. Okay, we have our alternative facts here. And Bob says, look, Alice, we can have a civil conversation about zeta functions, but your cool identities are just wrong. Maybe string theorists can get away with this nonsense, but if you keep saying stuff like 1 plus 2 plus 3 plus ... is minus 1/12, you will lose all your friends. You will spend your life sad and alone. Okay. So just to get a sense of this, the last time you had this conversation, how many of you were on Alice's side? Okay. How many were on Bob's side? Okay, it's an even mix, Okay. All right. And by the way, in case you think I'm exaggerating about this once every 5 minutes, I tried typing this into Google, and you see some of the results get up. Here are these videos. Outstanding fact. Here's debunking 1 plus 2 plus 3 is minus 1/12 debunked. Here's Ramanujan. Each of these videos has been viewed millions of times. So if you just think, yeah?
Every mathematician, on average, 100 times had this conversation.
Yes, is that right?
Students view this, right? Or the
you think I manipulated the number? Well, the thing is, it spreads. It starts maybe in China, then spreads to South Korea, and you communicate. I mean, it can spread by phone even. It's a very dangerous thing. But yeah, I mean, really, once every 5 minutes, that's only 100,000 times a year. So even if only a small fraction of these viewers are talking about it, this conversation is being had a lot. You see here Scientific Americans weighing in, Smithsonian, the great debate over whether. There's a great debate about this. Quora is having the debate. New York Times, they have this nice picture with rabbits labeled by the integers and a hat and minus 1/12.
So how do presidential candidates stand on this question?
I think it's only a matter of time before the Republicans take one position and Democrats take another, and they go back and forth on Twitter arguing. I can only imagine that's coming at some point. Okay, so for now, right, what do we make of this? Well, let's continue the conversation. Eve comes along. Pardon me, but I couldn't help overhearing. Ramanujan described a similar discussion in a letter to Hardy. Dear Sir, I am very much gratified on perusing your letter of the 8th February, 1913. I was expecting a reply from you similar to the one a mathematics professor at London wrote me, asking me to study carefully Bromwich's infinite series and not fall into the pitfalls of divergent series. I told him that the sum of an infinite number of terms of the series, 1 plus 2 plus ... is minus 1/12 under my theory. If I tell you this, you will at once point me to the lunatic asylum as my goal. Okay, so this is over 100 years ago, Ramanujan taking the role of Alice, and this professor at London, unnamed, taking the role of Bob. And apparently, this equation, when he sent it to Hardy, was one of the reasons Hardy was able to know that he was not a crackpot. He saw this 1 plus 2 plus 3 equals minus 1/12, and he kind of knew this came from the zeta function, and he knew that, okay, this guy is, maybe I can't verify every word he's writing, but, he's onto something. He's thinking some important thoughts. Okay, so where do we go with this? So Alice, I think we need a new crypto protocol. Yes? And Eve goes on and says, okay, a Laplace-Beltrami operator on a compact Riemannian surface on functions modulo additive constant has eigenvalues lambda 1, lambda 2, lambda 3, dot, 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 etc., growing approximately linearly. Okay, so you all know this if you working on the torus. Say it's just a 2 pi by 2 pi torus. What are the Eigen functions of this thing? Well, it's just your like e to the I, let's say a times x times e to the I, b times y, or something like that. And the Eigen functions, eigenvalues are just a squared plus b squared. And the number of eigenvalues less than r squared is, it's about what? The area of this thing, pi r squared or something, right? So basically these lambda j's are, if you put them in order, they're clearly growing roughly linearly in J. And that's true, Bayes' formula, this is kind of true on any two-dimensional compact manifold, that you have these eigenvalues that are discrete and they're growing roughly linearly. So we could apply this theory to those. And so it says, look, naively, this operator is going to have trace given by the sum of the lambda j, and that's infinity, and the determinant is the product of the lambda j, which should be infinity. But, as Alice said, an alternative, which was first introduced by Ray and Singer in 1973, is to just define the determinant to be of the Laplacian to be e to the minus z prime of 0, where z of s is the sum of the lambda j to the s, analytically continued. And by the way, the z prime, the delta prime, we sometimes put a prime there to remind ourselves that we're excluding the 0 mode. Or you can imagine it that we're working on functions modulo additive constant. Okay, either way. Okay. And so Eve says, well, to justify this, let's try to relate the determinant of the Laplacian to loop soups, certain random collections of loops that are related to Gaussian free fields, certain random functions, heat kernels, that some of you know about, and random surfaces. These were all the things that Laplacian determinants were made for. And this story will involve Riemann, Ramanujan, Ray, McKean, Singer, Polyakov, a whole bunch of other people who've worked on random surfaces and topics related to this in both in physics, in probability, as well as in geometry and analysis. Okay. So, all right. Well, here's the story. So first, remember planar maps. So if I give you a sheet of paper, you can, draw some lines and cut it into 12 squares. Take some glue and imagine you start gluing an edge of a square to a neighboring square. Okay, I've got 12 squares here, which means 48 edges, which means there's, 47 times 45 times dot, 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 a number of ways to match up these pairs of edges, each one to another, glue them in the orientation-preserving way, and try to make a surface. That'll be a compact surface, a manifold, well, with maybe some singularities if you have points where corners are coming together. But you made yourself a surface this way. And here's an example. This was made by Bertrand Duplantier out of actual physical paper with triangles. And the question is, well, what's the typical quadrangulation when the number of faces is large? So here's something, a picture produced by Marquardt, where he chose a random quadrangulation with 25,000 faces, and it's chosen uniformly among all the quadrangulations that give you a single simply connected surface. Okay, so a number of them end up giving you the surface. And he chose it uniformly, and then he put it into some software that takes a graph and tries to embed it in the three-dimensional plane in a kind of a way that doesn't stretch, has some algorithm for trying to make sure things aren't stretched out and distorted too much. And it puts it in, and then it's projected onto a plane, and you can kind of see the structure. So this is something that's topologically a sphere. You've glued all these things together, but it really has a crazy fractal structure to it. Okay, so it's very much less regular than a regular sphere would be. Okay, these were first studied by Tutt in the 60s when he was working on the four-color theorem. You can do it with triangles. You could think of these as random Riemannian manifolds with just singularities at the corners. So it's known this converges in law, in the Gromov-Hausdorff sense, to a random metric space that they call the Brownian map. So there is a continuum version of this picture that's known as the Brownian map. It's a random metric space. And this was established by all these people listed here: Chaseng, Schaefer, Legal, Paulin, Mirmont, various different papers. They did parts of this together. And there's some higher genus work on this, announced by Mirmont and Bettinelli. And there's this whole string theory program by Polyakov and lots of other people. And sort of the general onsets here was to say, imagine you have a map decorated by a function from vertices of your map into RD. Okay, so I give you your graph, whatever it is. It's some, maybe it's not exactly a grid, it's some funny graph. And I imagine that I have a map from this thing into RD. Okay, so every vertex is assigned D numbers, telling you where the point lives in RD. And so morally, you can think of that as the map being somehow embedded in RD. Okay, and there's I think, a certain physics motivation. Originally, if the story was you wanted to think of the time evolution of a string, and as it traces out a two-dimensional surface. And so I said, well, if you want to do like a Feynman path integral, maybe you want to integrate over all the possible two-dimensional surfaces embedded in RD. Okay, maybe D is 4 for space-time, or maybe it's 10 or 11 or 25, or I don't know. There's some number for D. Okay, and so it was natural to think about, let's choose not just a random surface, but a surface together with a map from that surface into RD. And the story was, well, if you can decorate this by points in RD, you could maybe choose a map decorated by a spanning tree or an Ising model or something. There are a lot of different combinatorial games you can play with these things. All right, and the Brownian surface program is to say, let's just understand the D equals 0 case very well. So we're not worrying about embedding this to any space. We're just looking at all random surfaces. And that was the original story. Okay, so if you want to start understanding this story, the first question you might ask is, how many ways are there to embed a map into RD? I describe the number of embeddings. Well, I mean, there's an infinity of them because there's a continuous space of them. We want to somehow describe something like the volume of the set of ways of doing this. Well, what do we mean? Well, somehow between nearest neighbors, maybe you want to put like a Gaussian, like a spring or something, holding them together so that you weight by e to the minus the difference between two neighboring points. And so if you sort of weighted by that, how many ways would there be to do it? Well, so let me say this a different way. So if I just take here's a Gaussian integral. Like, what's 2 pi to the minus 1/2 times e to the minus 7 x squared over 2? Well, we know if the 7 weren't there, this is just 1. So you put the 7 there, and it just, it's rescaling thing by a factor of 7, and this ends up being 7 to the minus 1/2. Okay, that's like 1 over the variance squared. And, well, so if you want to do this in higher dimensions, you just take that number 7 and replace it with a matrix. Okay, so what's, the integral of 2 pi to the d minus 2 times e to the minus x dot product with a of x. X is some matrix over 2. And, the same simple argument tells you, if the a weren't there, this would just be 1. And if the a is there, you end up having this determinant of a to the minus 1/2 that comes here. And we refer to this determinant a to the minus 1/2 as the partition function of this thing. And it's telling us somehow, if you like, determinant of a to the 1/2 is the height of the normal density function at the origin. Or if you like, the determinant, this is like the integral of this thing if you normalize it so that the value at the origin is just some constant, like it's 2 pi to the minus 3 over 2. So if you normalize it that way, then when you integrate, you get this. Okay? And, the way we kind of think of it is if I gave you a graph, maybe one looks like this and one looks something different. Maybe I give you some graph where maybe I want the same number of vertices. I don't know. I give you like a couple of different graphs, and let's say I set them up so that they have the same number of vertices, maybe the same degrees or something, and but they're different graphs, and I want to know sort of which one has more planar maps associated to it. Well, I could imagine that I divide each edge into a billion pieces, and I say, okay, the function from this thing into the plane has to be such that every piece maps as you go along these edges, you just change by plus or minus 1 at each stage. So you have this path where, it'll get embedded like to some crazy picture like this, where each vertex maps to a point, and then in between the vertex you have some sort of thing where in each coordinate it's just going up and down by plus or minus 1. And then it would just be a simple counting problem. But then this would just be kind of like approximately a Gaussian, because the number of ways to fill this thing would be like, just by central limit theorem, it's roughly e to the minus the distance between the two endpoints squared. And so if I were counting the number of ways to embed this, it would really be like this quantity here. And when you work out what that is, it's approximately this determinant. Okay, so morally speaking, in some sense, this determinant to the minus 1/2 is the number of ways to embed a planar map into the plane, into RD. What's that?
What is A?
So A in this case is going to be the determinant of the Laplacian. Okay, and the important thing is that if I take a function h, and then I take the inner product with minus the determinant Laplacian of h, this is equal to the L2 norm of the gradient of h. So somehow I'll say gradient of h squared, right? So somehow
the surface you form by gluing together the squares or the triangles?
Yeah, this is just the graph Laplacian, the Laplacian on the graph.
Right.
So right now this is all just discrete. There's a continuum version, but for now it's just discrete. Okay. So and this, I mean, this is kind of a simple discrete integration by parts, or you can use it by using the fact that the Laplacian can be written as the product of like the incident matrix, the gradient matrix, and its transpose. So the gradient is a linear operator, right? So it has a matrix from r to the number of vertices to r to the number of edges, and so if you just take that times its transpose, you get this Laplacian, and so it's kind of a simple argument to see that these are the same. Okay, so if you want to weight by e to the minus this, which is what I would describe with this picture, effectively you're weighting by e to the minus this, and so somehow the number of those should be like the determinant of this thing here, which is playing the role of A in the story up there. Okay. So, right, so the Laplacian, just to remind what this is, if I give you a graph V, E, it's this linear operator where its matrix is, it's 1 if I is not equal to J, and 0, and the edge is not there. The edge is there, 0 if the edge is not there, and it's minus the degree of VI whenever I is equal to J. Okay, and so if R is a set of functions with mean 0 and the Laplacian is invertible, then Kirchhoff's matrix tree theorem says that the determinant of this Laplacian is, well, some constant, let's think of, size of V times the number of spanning trees of VE. Yes?
Complement of R. I'm talking about complement.
Delta operates on...
Oh, no, sorry. You're right. That's right.
Oh, yes. Right. Okay. Right. Yeah, so R is the complement to the set of constant functions. But yes. I was worried actually presenting this slide with Russ in the audience that I would make a mistake because I'm sure matrix tree theorem is something he knows much better than I do. But yes, that's correct. So this determinant Laplacian does two things for us. One, if I take it to the minus 1/2, it counts the number of ways to embed this thing into RD. But if I just take the determinant itself, it counts the number of spanning trees I can put on this. So any graph, it's connected, means I can find at least one spanning tree on it. So just a subset of the edges that has no cycles and includes every vertex. And this, the number of these trees is also this determinant thing. Okay, so this is a nice story. And okay, and so then again, the discrete Gaussian field partition function, we think of it as a number of ways to embed, and that's its determinant to the minus 1/2. Okay, so why do I care about this? Well, sometimes they say, I don't really want just a random planar map. I want a random planar map with an embedding into RD. I want the random embedded map. So instead of saying all planar maps are equally likely, I say all embedded planar maps are equally likely. Okay? But if I do that, then the probability of a given planar map should be proportional to its number of embeddings. Okay? So I can say I want the probability of a certain graph to be proportional to say the determinant of the Laplacian on that graph raised to the minus d/2 if I'm imagining the graph is a random graph embedded in dimension d. Okay? But then the story about this is you say, well, if instead I took a graph decorated by a random tree, then that would be the same thing as taking d equal to -2. So they say a random graph embedded decorated with a random tree has the same behavior as a random graph embedded in dimension -2. Okay, so the latter thing doesn't actually make any sense, but this makes perfect sense. I can take a probability of graph proportional to this. I can put any d up here, including non-integers. Okay, and so the story is if I took a graph, weighted by, if I take a random graph with k spanning trees and d copies of the Gaussian free field, then I would just I would be effectively weighting my graph by this to the minus d/2. This where this is the number of Gaussian free fields, and then I would have to add maybe plus c over or some constant over times, or just some constant here where somehow this would be like number of Gaussian free fields, and this is like number of trees. And when I say Gaussian free field, I just mean one component of this embedding. So this just means d real numbers. Yes, go ahead.
Can I just do a little reality check to see if I'm following along?
Yes.
So in the third from bottom bullet point, you say the determinant is about the number of vertices times the number of spanning trees. Mm-hmm. So I would think that for most of these maps, that would be a pretty big number. Lots of vertices, lots of spanning trees. Is that right?
Yeah, that's correct. So it should grow exponentially somehow. Yeah.
The number of ways to embed is 1 over the square root of that large number. So that's pretty close to 0, right? So it says that there's almost no ways of embedding into the...
It's a weighted number.
Yeah.
Is that right, or am I...
The thing is that this this number of ways is in quotes. Maybe those should be... They cover a multitude of sins, yes. So it's not an actual number. It's more like a volume, or it's this integral, or like Strauss has a weighted number. So it's.
But the bigger and more complex the map is, the smaller that thing is.
Yes, correct. That's correct. Right. Yes. So here's another way of thinking of it. So a determinant is the number of spanning trees that's minimized if the map is itself a tree. Right? Tree has only one planar map. And so intuitively, somehow, the less tree-like M is, the larger the determinant of the Laplacian. So somehow you think of it as, if I give you a tree, there's only one spanning tree of it. On the other hand, the Gaussian if you look at the embeddings, it has a lot of freedom because every edge can sort of independently do whatever it wants. There's nothing that has to be joined up. There's no cycle where but if you had something with a lot of cycles, then that would give you a lot of freedom with your spanning tree, but then you'd have less freedom with your Gaussian field because things, when you go around a cycle, you have to end up in the same place.
What if you have no embeddings?
Correct.
If you have no embeddings, well, the thing is, for the kind of embedding I'm thinking of, you always have an embedding. Because when I say embedding, I just mean a function from the vertices to the real numbers. So, yeah, so it doesn't have, the edges are allowed to cross. I'm not thinking of it as an embedding in the strict sense. Yes, good question.
Well, earlier we heard a talk in the conference about embedding graphs, like with bi-Lipschitz distortions, but that's not the...
That's not exactly what I'm doing here. No, I mean, it's... We like the metric structure, but yeah, that's not exactly what we're working on. Right. Okay, so tree-weighted map. So if instead of choosing a uniform planar map, I choose a tree-decorated map MT, the marginal law of M gives M a probability proportional to this determinant Laplacian. So again, M tends to be less tree-like than in the unweighted case. So I'm viewing, remember, tree-like means very few spanning trees. So here I'm waiting to make it less tree-like. And for these Gaussian field-weighted planar maps, I'm choosing a map weighted by d instances of the free field. Then this should somehow make it, weighting by this should make it more tree-like somehow. I'm making it be closer to being a tree. Okay. There's another story. If I fix a boundary vertex, there's something, a loop measure, so here I have to explain a little bit what I mean by this, but somehow it's possible to describe a Brownian motion on the graph itself, where each time you come into a vertex, you kind of randomly decide which direction to exit out. So you just get a bunch of Brownian excursions from the vertex, each one randomly choosing one of the directions until at some point you reach the next vertex. And so there's a Brownian motion on this graph, and it's possible to take this Brownian motion and form a little loop. So you go for some amount of time, then you come back to the origin. Okay? And it's possible to put a measure on these set of Brownian loops. And it turns out if you take the natural way of doing this measure, you can take mu of the event p is greater than 1, where p is the number of vertices that is hit by your loop. So mu will be the loop measure. So basically it means I'm only looking at the loops that hit at least two different vertices. I'm sort of ignoring all the small loops that hit only one vertex. And here's the nice story here. If I were to give you a second graph that, let's say, it has the same vertex degrees as this graph, the same number of vertices, but it's a different graph, that means I can map the vertices on here to here in a one-to-one degree-preserving way. And so any little loop, Brownian loop I get over here, on one of those vertices, I can just map it to the corresponding loop over here, as long as it's a loop that only hits one vertex. So all sort of the small loops are sort of in one-to-one correspondence. They don't depend on the graph. They just, once you fix the degree structure. On the other hand, if I look at the big loops, the loops that hit multiple things, well, those are more interesting. Those depend on the graph. Okay? And so this sort of says that if I ignore all of the small boring loops that don't care about the graph, then this measure of loops is exactly minus 1/2 the log the determinant. Okay, so it's sort of the log of this thing we weight by when we put an instance of the Gaussian free field, when we put this random embedding on this map.
Loops go through the boundary vertex.
So the loops live on the graph itself, but they go along the edges of the graph.
How do you choose a boundary vertex?
Yeah, okay.
You don't want to?
Well, I put a boundary vertex there because if you don't put a boundary vertex, the loop measure is infinite. It turns out you have a lot of really long loops. Well, I just forgot to say that sooner, but you're right. So what I do is I take one vertex and I say, we're not going to allow any loops that hit this vertex. So throw out all the loops that hit that vertex. And now, if I throw out the small loops, all the reasonably sized loops, the measure of that will be this.
Well, earlier in the week, Russ Lyons had emphasized that, like when you're trying to pass from finite to infinite graphical objects, it was really important to root them.
Yes.
Tightness, is that the same thing sort of going on here?
I mean...
Since it's his birthday, you can say yes.
Okay. Anything for you, Chris. No, I mean, it's somehow, I think we know what Russ was talking about is maybe sort of a combinatorial phenomenon that, if you have it with a root, it sort of gives you a place to start looking if you want to sort of describe what the thing looks like. Whereas here, I'm putting a root because I really don't want to count exactly all the loops. I just want to count the ones that avoid this. And it turns out that the answer doesn't depend on where you put the loop. That's maybe not that obvious. But yeah, that's the...
Well, also, if you insert a boundary vertex which is not hit, you're sort of like imposing a Green's function on the system.
Yeah.
Very long things are going to stop because
That's right. That's right. So very long things are very unlikely. I mean, having a loop live is somehow exponentially unlikely in the length of its life. So you're sort of eliminating all the large ones. Okay. And so I say this again, so somehow requiring p greater than 1 effectively truncates away the small loops. And since paths are killed when they hit the boundary vertex, the long loops are exponentially rare. Okay. And these are some of the mathematicians who are responsible for this statement and a lot of work in this area. Okay, so
It feels like a soup. Yeah.
starting to feel like a soup.
Oh.
Well, and so here's where specifically, so Wendelin coined this term, loop soup. And he said, loop soup of intensity C, what you do is you take it's a random loop decorated map as follows. So given a map, the loops are a Poisson point process where the total number is Poisson with parameter given by C times this measure of loops, mu p greater than 1. So somehow, if I have a measure, I can choose a Poisson point process from that measure. So it means to every little set of tiny size epsilon, I have something in that with probability roughly epsilon. And so on a larger set, the number of points will be Poisson given by the measure. This is like, you don't know Poisson point processes. It's like if rain is falling and you look at a unit square of sidewalk and you wait until you would have expected one drop to hit that unit square, then the actual number of drops you see is going to be this Poisson random variable. And if I give you any region of area A, then the number of drops that hit that region will be Poisson with parameter A. And but here, instead of taking a sidewalk, I'm taking this loop space. So it's a space of all loops. And then I'm putting down random points here. And putting down random points means selecting a collection of loops. Okay, so I end up with some random collection of loops. And that random collection of loops is what Wendelin started calling the loop soup. Okay. Now, somehow, so given there are k loops, the map probabilities are going to be proportional to this c times the number of loops to the k. And overall, I'm going to take the probability of a map to be proportional to the intensity c loop soup partition function, which is e to this c times this loop measure, which is this determinant applying to the minus c over 2.
Why are map probabilities related to the number of loops? Or what is the connection between k loops and map? What's the connection between map and k?
Well, so what I'm going to imagine is that instead of choosing a map decorated by a tree or a map decorated by a function to RD, I'm going to choose a map decorated by loops. And so when I choose a map, I say I'm not going to choose all maps equally likely. The probability of a map will be proportional to somehow the number of loop soups on it. But number of loop soups means this partition function, it means e to this loop soup measure.
Decoration of the map.
So that's right. Okay.
So a map with lots of short loops, like a grid, that's more likely than something more tree-like.
Yeah. So somehow if I condition on there being 0 loops, then all maps are equally likely. But given any map, the number of loops will be Poisson with parameter given by e to the or given by the loop soup measure of that thing. Okay, and so those two facts require that the probability of any map is proportional to this e to this loop soup measure, which is exactly this determinant Laplacian to the minus c over 2. Okay, so which means that I could also put over here a plus c, and c is going to be the somehow the what did I call it? The loop soup of intensity. This is the intensity of a loop soup. Well, I guess this is minus c over 2, right? So minus c over 2. So somehow I can decorate it by free fields, trees. I can also decorate it by loops. And I can do that for any value c, and that makes sense. Okay. And again, I can tune this parameter c I can increase it to make m more tree-like, or decrease c to make m less tree-like. I have this parameter. And the belief is if c is equal to or greater than 1, then this makes the scaling limit something that we sometimes call a Liouville quantum gravity surface with this parameter gamma, which is, well, don't worry about exactly what it is, but it solves these things where q is 2 over gamma plus gamma over 2, and c is 25 minus 6q squared. So it's somehow that determines it. And so as c increases from minus infinity to 1, this value gamma increases from 0 to 2 over this range. If c is bigger than 1, then the naive constructions give you somehow, it starts to look more like a continuum embedded tree. So it starts to look so tree-like it's actually a tree. But there's a way to make sense of this even when c is bigger than 1, and you get something like a certain type of branching process that's kind of an infinite volume. So I won't say too much about that here. Okay. Another way to think of what's going on here is if I give you any planar map, you can measure the size of the planar map in two ways. One is you just count the number of edges. Let's put that on this axis. And the other is I take log base 2 of the number of spanning trees. Okay? The number of spanning trees is at most 2 to the number of edges, right? Because each edge is either in the tree or not. So somehow, if I were to plot, I put one dot for every map. Then, the dots on this bottom line would correspond to the trees. They're the most tree-like things where you have, the only one spanning tree. Log of the number of spanning trees is 0. And then the ones up there higher would be the graphs that have a lot more spanning trees, the sort of more interesting ones. And I imagine that I put one dot for every point. Well, if I just choose a uniform random map weighted by the number of edges, I'd be choosing like a random thing from one of these columns. If I say, okay, I want a random map with 100 edges, I just pick one of these columns and choose one of those. But then if I weight by the number of spanning trees, that's sort of going to be pushing me up to a higher or a lower position along this line. And effectively, sort of the typical object will be like taking things along one slope, and when I do the weighting, it sort of pushes me up to it changes the ratio to some different value. And that's sort of another way to visualize what's happening when I tune this parameter c. I'm going from points, roughly speaking, along a line of one slope to things, roughly speaking, along a line of a different slope. Okay. Now, so there's another story too. Somehow adding other critical statistical physics structure is thought to be more likely like adding loop soups of some intensity c. So, and this is something that's really not proved in nearly as satisfactory a way as we would like, at least not in this story. This is, Stas, who's here, is responsible for a lot of what you would consider satisfactory results about, really proving how the Eigen model is related to these, these various conformal invariant quantities like determinant Laplacian. But for random maps, there's really a lot we don't know. But the general story is that if instead of weighting by free fields, loop soups, and Eigen model, or trees, I weighted by an Eigen model. So an Eigen model is basically I'm assigning everything a spin plus or minus 1, and somehow weighting by putting a weight that makes them want to agree on neighbors. There's a certain model. Don't worry if you haven't heard of it before. But somehow weighting by that is supposed to be kind of like taking C equals 1/2 here. And weighting by determinant Laplacian to what would then be, I guess, the -4th power. Okay? And so it's not obvious, because in this case it's not exactly true that the partition function of Ising models is exactly a power of the determinant Laplacian. It's just somehow believed that in the limit, when you weight by it, it somehow behaves as though it were a power of the determinant Laplacian. In terms of the limiting properties of this map, it somehow is like that. And there's something called the FK random cluster model, where you can tune a parameter and get a whole range of C values. There's something called bipolar orientations, which correspond to C equals -7 somehow. Something called Schneider-Woods. You decorate by this other combinatorial structure, which corresponds to C equals -25/2. So various students have done these things. A spanning tree, -2. Discrete gas-free field is again C equals 1. So all these things, when you decorate this by some model, and instead of choosing a random graph, you choose a random decorated graph, adding that decoration somehow morally corresponds to just changing this C parameter. That's the story.
So when you have a name there, that's a theorem, and otherwise it's a prediction? Or?
Well, these things here are, the last two are identities. These are just algebraic facts. This is the Kirchhoff's matrix tree theorem, this one here. And this one here is just, well, it's just the definition of determinant. It's just that scaling property of the, so these things are, and this loop soup thing is, well, all those names I listed before. Okay, we're going on Alice. You're taking longer to get to the point than I anticipated. Bob, yes, I think we already believed that loop soups, Laplacians, determinants, and GFFs were all related on discrete maps. Alice, we all know that uniform random planar maps scale to Brownian surfaces. They'd heard that portion of the story before. Bob, and loop soup decorated maps should scale to Liouville quantum gravity surfaces that are either rougher or smoother, more or less tree-like, than the Brownian map. SC is respectively positive or negative. Big C means that you have a super rough surface. C close to minus infinity means a smoother surface, although still fractal. And Alice says, yes, in fact, as far as I know, the Hausdorff dimension of this surface as a function of C, it's a big open problem, but it's believed that it should increase from 2 to 4.8 or so as C goes from minus infinity to 1. There is some amazing new work about the metric structure of these Liouville quantum surfaces. Here's a bunch of people who've worked on this. Eve says, yes, right. Alice, but you haven't mentioned continuum loop soups or zeta functions. Eve, that's coming. Bob, can you just show us the theorem? Alice, or maybe first some more pictures and then a theorem. Okay, so we side with Alice on this. All right, so let's do the pictures. So more pictures. So for pictures here, we'll skip past the rabbits this time. Here, if you just Google random planar map, you get a whole bunch of pictures. And I want to go to one in particular. This is from Jeremy Bettinelli's webpage. And he's had these nice things. This is kind of like, this is one of these random planar maps I showed you before. But you can spin it around. See how cool that looks? And here's one of them where he conditioned it to have genus 3. So this is the question that I'm sorry I wasn't around to answer this morning. But what do you make of these higher genus ones? In the compact case, you can take a uniform surface with some particular topology, and it's supposed to look something like this. And there are non-compact versions, if you like. But
these look embedded.
What's that?
These look embedded.
Yeah. So basically, they took some software that put the embedding, but the way it's embedded is not. It's not by this sort of kind of random embedding I'm describing here. It's by once the map is given, this software is just embedding in a way that makes it easier for us to visualize what the surface looks like. So this isn't sort of like the string theoretic embedding. This is sort of just embedding that lets us see what the structure of the surface is. Here, this is a surface decorated by by one of these bipolar orientations, which corresponds to c equals -7, which means it's a smoother surface. So this is like surface embedded in dimension -7. So it's somehow a less tree-like surface. It's smoother, which you can clearly see on this thing, right? Some nice little creature. Now, this thing here is a much more tree-like structure. So they weighted it by something that was going to make it much, much more like a tree. Okay? So you have these different directions you can go with this thing. All right. So now getting to this theorem. So first, pre-theorem definitions. Okay, so for a Brownian manifold MG, possibly with boundary, and a curve, we define the duration of the curve to be, well, this half of the quadratic variation. So this is like a Brownian curve. So you can measure its duration that way. If G naught is any metric and G is e to the 2 sigma G naught, then I can relate the somehow length of a curve on one metric to the length on the other. So the length on the other is be this integral 0 to t of this kind of change of metric factor dt. And so this Brownian loop soup measure is defined, I talked about it being defined on graphs, but you can find it on random surfaces too. It's a random collection of loops, Brownian loops. And you can write this mu loop mg for this Brownian loop measure. And on any two-dimensional Riemannian manifold, this loop measure is infinite because you have a lot of loops of short duration. So if you want to handle the short loops, you need a way to truncate away the infinitude of small loops. So remember before on a graph, I just said throw away the loops that only hit one vertex. Here we have to find another way to do it. Okay, so here's this theorem, and I put our names on it, although to be fair, I have to admit that most of the work of this theorem was done by people before us. We're sort of adapting it to our language and putting it in the language of loop suits, but very closely related things about determinant, heat kernels, determinant Laplacians, and things like that came by people like Sarnak and Ray and Singer, like I mentioned. So there's been some work on this preceding us. But basically, this is what the theorem says. Okay, if you take a small delta greater than 0, then this loop measure, so this is, the loop measure, the measure of the loops on the manifold G with length greater than delta. So this delta here means I'm truncating by delta, I said before, is given by, is the volume of M divided by 2 pi delta minus the length of the boundary divided by, well, constant times delta, minus this determinant Laplacian. And then I have these other terms that just depend on delta, these kind of logarithmic terms. And basically, if you look at this thing, if I fix the volume of the surface and the length of the boundary, the only thing in this surface that depends on the manifold is this one term here, this minus the log determinant Laplacian. Okay? So somehow, when I take delta smaller, I'm obviously getting a lot more loops because I'm allowing all these small loops to be there as well. And so it's blowing up. But nonetheless, if I were to compare two manifolds with the same boundary length and an area to each other, what I would find is that they have very close to the same loop suit measure. Very close to the same measure of loops. And the only difference comes from this little constant thing that's related to this determinant Laplacian. Okay, and if you like, this is a very geometric description of what the determinant Laplacian means on a manifold. Okay, and this, for a long time, this sort of bugged people because you couldn't really define a discrete Gaussian free field on a manifold, that in a way that wouldn't, that would allow you to just see this constant order difference. Spanning trees, well, you could try to approximate your surface by a tree, but it wasn't clear how to do it where you would get the right count. And here it's saying if you do a loop hoops, you really get asymptotically this kind of exact statement here. Okay. If you do it on a compact surface without boundary, you get something very similar, where, so here I'll take the loops and I'll truncate at delta, and then I'll also truncate at a large value c. So there are loops size between delta and some large value c. And then I end up I can truncate by this log c, and then I have, all this, the only term that really depends on the shape of the surface is this log determinant Laplacian. Okay. So, and so I want to point out just kind of how crazy this is. To tell you, if I give you some...
Between the manifold and the loop soup on the graphs.
Well, so...
The measure is related to that. But
yeah, so basically this loop soup on a graph, you can define it on a manifold as well. So if I just replace the graph with a surface, then I can define a loop soup on that surface. Okay? And so what's going on here is if I take a surface, some crazy surface like this, and then I take another crazy surface of the same size, and then I truncate by some small delta, what I'll find is that these essentially have the same loop soup measure for small delta, except for this constant difference, which is this. So if delta is 1 over a billion, then the measure is about a billion on this side and about a billion on this side. But there's this constant order error of difference. So this is a billion plus a constant, and this is a billion maybe plus a different constant. Okay. So and so if I choose one thing where I weight by the loop soup measure, by e to the number of loops, I'm weighting one of these by slightly different, a constant more than I am this other one. So somehow if I choose a random surface decorated by this thing, I'm in a very subtle way favoring ones that are more tree-like or less tree-like. Okay, and so what we've done, okay, and I'm about out of time here, so I just want to say, the upshot. So let me say we're saying this thing has a discrete analog, and I just okay. This is all very unimportant, the stuff I'm skipping over here. This was clearly just filler. This is an overview of the proof of the statement. And so here I want to say that if you look at these random surfaces, there's a way to make sense of taking a space and breaking it up into squares that all have the same size with respect to this random metric. So I can formally map the metric to a sphere, and then I break this space into squares that have the same size with respect to that random metric. And if I use this and do a sort of smoothing operation, I can make a sort of smooth surface that is believed to be a scaling limit of these surfaces here. Okay? And what I find if I take these smooth surfaces that somehow are morally similar to these surfaces, since they have the same limit, the same Liouville quantum gravity in the limit, that if I decorate those, these approximate Liouville quantum gravity surfaces by loop soups, the effect of that is exactly to change this parameter c. Okay? So there's an approximation for these continuum random surfaces where putting the c weight exactly just moves you along this parameter. So when I alter c, it just shifts me along this spectrum from more tree-like to less tree-like in a very exact way. Whereas here, it's somehow, we for these discrete approximations, we kind of know that some of these discrete approximations converge to Liouville quantum gravity in some sense, but we don't know that the GFF weighted versions, the weighted versions of the discrete guys, converge to the continuum analogs. Okay, so that's a lot to absorb in the last couple minutes, but I hope I got through at least this determinant Laplacian story, and I'll end there.
Questions?
Yes.
Can you go back to your theorem, please, with the area and the length?
Yes. Let me go back to that. That's
right.
This here, yes.
So when you put this up, I was shocked, because I've been more or less staring at this equation the last year.
Yes, okay.
But it was in a different context, something called renormalized area.
Yes.
So there we have a surface in, say, hyperbolic space, and we want to compute its area, but it's infinite.
Okay.
So Whitten and others have suggested when you truncate delta from the boundary, you take the area of that truncation and subtract the length, and then take the limit of that as the truncation goes off to infinity. And there's a formula for that, which involves the Euler characteristic of the surface and the difference of the volume and the length, and then the leftover term is renormalized area, except here it's the low determinant of the delta.
Okay.
All the terms have analogs. And
I see.
I'm wondering if that was a coincidence, because there's only a few ways to write equations down.
Okay.
There might be some kind of connection.
Um,
So you're familiar with the renormalized area idea, or?
no, I guess I'm not.
It's saying the isoparametric inequality holds with an additive constant that in hyperbolic space, volumes and areas are sort of proportional.
Oh, okay, I see.
And what if you ask a stronger thing that they're actually within an additive factor of each other?
Okay, I see.
So this is when you take a volume and subtract a length, do they stay within an additive factor as?
Yeah. Well, so what will I say? I mean, will I say what is going on is that if you take, say, a surface with boundary, and you look at what are all the loops of size delta for some small delta? Well, small delta, they're all just sort of little loops in the surface. And it sort of makes sense if you're just looking at little loops. You double the area, you just have twice as much space to put these little loops. So you should double the mass of these area delta loops. And it also makes sense that on the boundary, there are some loops that would hit the boundary and you're sort of losing them. So that somehow the boundary, the length of the boundary gives you fewer loops. And so this basic idea, you could replace these loops with just balls of the right area. And so if you were doing just that, then it would be something like what you're saying here. And so somehow, we're not really interested in the little loops. We're interested in kind of, all the sort of macroscopic loops somehow. And so this is sort of this, the zeta function regularization, it's sort of equivalent to truncating away the small loops and taking the limit in the right way of the loop measure.
Because the form of the equation looks almost identical, plus this renormalized area is very closely associated to what's called the Weil-Pearson curves in the plane, which themselves can be characterized by the chance a loop soup hits them.
Okay.
You take a curve and you take its approximation, you take a conformal retraction of it, a equipotential line, and the chance the loop soup hits both the curve and this equipotential thing gives you both this renormalized area and the linear energy of the curve, and then it's coming up here too, which is also a loop soup thing. It just seems you can't get away from it. It's just the same thing over and over again.
Yeah. Okay.
Oh, great talk, by the way.
Oh, good. Thank you. Yes.
In the case of the square torus, what's the negative log that of the determinant?
In the case of the square torus, I'm not sure. I'm not sure. I'd have to. My graduate students would probably know it off the top of their heads, but I can't remember exactly. But I'm sure it's computable. Yes.
You're mainly talking about central charge less difficult than what, right?
Yeah, I mean there is this story. So I didn't show this, but there's this paper that some of my students wrote about making sense of this Liouville quantum gravity where the central charge is between 1 and 25, or the matter central charge they call it. So there is a version of the story that makes sense for larger values, but it's a little bit different. Essentially, this argument, this idea of weighting by, this makes sense for any real number, d, right? You can make sense of this for any value.
They are totally independent, not correlated.
Yeah, but somehow it's believed that if you take this d to be too large, that in the limit it just starts to look like a tree. It starts to become kind of boring. So just what they call branched polymer.
So, do you see any way how maybe putting something else on the surface is
Yeah. So the way it happens is that there's a certain framework for, let's see, making sense of these. Where did I have these pictures of these squares? Okay, let me just say there's... no, the pictures were earlier. Okay, so there's this... Okay, never mind. I don't need the pictures. So there's this story where, I give you a square, and you have like this Gaussian free field on it, and you use it to help you decide what the size of each little square should be. And you keep subdividing a square until you get to some particular threshold size delta, and then you stop. And so the idea is that all these squares should be roughly the same size delta. Okay? And if you look at what that means in terms of the field, it's sort of, you're looking at the averages of this field, and you're plotting it against the number of increments, and you're sort of stopping when you hit a certain line. And the slope of that line depends on c. And it turns out that you can adjust the slope of the line beyond the c equals 1 spectrum, and it makes perfect sense. The only difference is that after you do that, you will have some places where the squares branch forever. Okay, so somehow the volume will be infinite.
And of singularities?
Yeah, you'll have singularities. A dense fractal set of singularities. Okay. Nonetheless, you really still can make sense of the surface. It'll just be kind of an infinitely branching surface, like a Galton-Watson tree, like a tube that branches into separate tubes. Those branch into separate tubes, etc. And so, what's that?
Still path connected?
We think so. We think there should be a notion of a metric on this surface, but we can't prove it. So one of our big problems is prove there is a metric space structure for this Liouville quantum gravity parameters between 1 and 25. So there should be a random metric space that corresponds to this structure. And it should be kind of a tree-like metric space. It's infinite diameter, because you have all these places where you go off forever. And we have some ideas about what discrete models might converge to these things in the limit. So they're interesting. It's something we're playing with. But it's true that if you restrict the size of it to be finite, then we think it does just degenerate. Like say, it becomes sort of boring. It only is sort of interesting when you allow these infinite volume trees. I don't know. Maybe we can talk more. But
what happens at 25? Does the singularities form loops and separate it into different pieces or something?
Yeah. So at 25, somehow you get to the place where these things would never divide at all, any of them. So once you get beyond 25, there'll be whole regions that just never divide ever. And so another way to think of it is, it's sort of you're weighting by this. You have like a Gaussian, and you're weighting it by something, and somehow at 25, these terms cancel, and you just get this exact. It's just constant. And then after that, you would get an infinite measure. We don't really have a good way of making sense of this as probability when you get above 25.
I want to thank you again for your talk. It's something I don't understand, but instead of feeling stupid, I feel entertained. And
Okay, that's all I was aiming for. Yes.
Thanks, Scott, again.
Okay, thank you.